as we talked before, we have different kind of memory in a computer. So you have your hard drive, and that's basically kind of like the persistent storage that you can save things and it's gonna remain there. We have the memory, and that's basically a volatile. It's called RAM usually. And also you have like some registers here or some cache on the CPU. So there are like very different types of memory. So here we are talking about the main memory or your RAM. And that's basically, it's a kind of a temporary memory. So let's say if you have a program and or application that is on your computer, so it's saved on your hard drive. So like the binaries or the executable or like all the files for that is actually on your hard drive. So in that stage, it's actually not running, right? It's like living in your hard drive, but it's not running. Once you run that program, it's actually loaded into your main memory. So that's become like kind of like a process. So that's like the distinction that um, when you have basically a program running, they're usually like in their memory, in your memory, because they have different information there. So part of it is like the code that is being run or executed, and then they have maybe some variables, they have some stack frames. We're going to talk about them more, but basically as soon as they're running, they have to live in your memory. And well, that's the purpose of main memory. And why it cannot be on hard drive? Because of the speed. So main memory is, we have a, as we talked about, we have less space or we have less capacity on that, but it's much faster than your hard drive. So that's why if something is real time, like a program that is running, it has to be in your main memory. And we said that it's volatile if it's kind of temporary, so you cannot save things there and like turn off your computer and come back and you have still things there. You could like dump that memory to your hard drive and then load that again. That's a different story, but on its own, it's volatile. And also, um, the memory itself is actually byte addressed. So basically means each location on the memory or each address on the memory, it's actually 1 byte. And here you see this helpful chart that is showing the relationship between like the byte and like let's say half word and a word. So 2 byte makes a half word and 4 bytes makes a word. And in this table, you can see actually how many bits is in each of them. The main things that we're gonna work with is, well, you have bit, which we talked about is a 0 or a 1. And then a byte is 8-bit put together. So you have 8 0 or 1s. And then you have a word that is 32 bits. So these are the main three things that we're gonna work with: a bit, byte, and a word. And so you can think of a memory on its own as basically as an array. So if you look at like a normal array in any language that you're working with, like C or Java, you have these indices, or you have an index for a specific location, and that's kind of like the address, or it's like a pointer to specific location, and that location has some content, right? So in the memory, it's exactly the same. So let's say this is your array, and so this is like index 0, index 1. So if you refer to this location as index 1, you have some data stored in there. So that index 1 is your address, and that content that is there, it's basically the data that you put in your memory. And as we said, each address is a specific address on its own is a byte. So there is byte address. So when you write on your array, like, so this is how you would do it in a normal programming language, right? So if you are doing Java, for example, you have this array, and then you have the index, and then basically here you have like another variable, right? So you have x equal to this. So it's gonna copy the content of this. Well, copy is a bit, debatable, but basically it's gonna take this content and put it into that variable. If you are writing to that location, you have it basically the other way. So you have some like x here or some content here, and that content gonna be written into this array. So in the memory, it's basically the same thing. In the hardware, it's basically the same thing, But what actually happens is that if you are reading from your memory, so here you see like you have kind of like a memory controller. So if you are reading from the memory, you are putting the address, basically that kind of like the index of the location that you want to read from, into some specific address pins on the memory controller. And then you have to put a flag that you are reading or writing. So you put this flag to 1, you put the read flag to 1, and in basically the memory controller will fetch that data from the memory and have the data to be on the read data pins. So you put your address, you say, I'm gonna read some data, and then it's gonna get you that data here. And then you can take that and do whatever you want to do with that. And then if you're writing, it's basically the same thing. You put the address first. So you're saying, this is the address that I want to write to. This is my data. So it's literally like some pins. And you will program in your assembly language, you can control this. Basically, you put your data also, and then you say, I want to write. And the memory controller basically sends that signals and write that on the memory itself. So it's kind of like a bit mechanical way of doing that. And okay, here we see actually, so as we talked, like we said, think of the memory as an array. So you have all these like different locations. And we said that it's byte address. So each of these are 1 byte of data. So if you are going from like 0 to 1, so here you have 1 byte and here you have 1 byte. So if you see also, we are incrementing by 1 every time. So 0, 1, 2, 3 is going all the way. And then a note here that is 9, and then A, and then B. So this is in hex, actually. So because we have a lot of memory and we want to be more compact, right? So if you remember, we said if you are putting something in binary, it's going to take like so many digits. If you put it in hex, it's going to be more compact. So usually the addresses of the memory we are using in hex. So you see here A and B we have that, so 10, 11, and so on. And then here you see the content of that. So in this address, you have basically a hex value, which is basically 1, 3 here. But that's, if you convert that to binary, we said that each of these digits are 4 bits, right? So each digit in hex was 4 bit in binary. So we have 4 bit here and 4 bit here. So total we have 8 bits. So you see that this one address has 8 bits of content. This second address again has 8 bits of content, and so on. And this is, again, it's just a representation, right? So the fact that I'm writing this in hex doesn't change the fact that on the memory itself is actually 0 ones. So there is like, we are representing it here like this because it's more easy to read and easy to write. So if you're looking at this versus looking at 8 zeros and ones. So there is a change here. So if you look at here, we said that we have this array and each of these are 1 byte, so 8 bits, and we are incrementing by 1. So from this index to the next index and so on. But actually this is still very like fine-grained, right? This is very small data. So what we deal with in a 32-bit system is that instead of having one address and having 8 bits, we are actually grouping these 4 together, and we're gonna refer it by the beginning address. And then it's gonna be, instead of being like 1 byte, it's gonna be 4 bytes together. So this was 1 byte. We put these 4 together and we just refer it by this first address. So the next one, we're gonna go here. So here, and then again we have 4 of these together. So that's gonna be 32 bits from this address, and then here we're gonna have 32 bits. So we're kind of like grouping them together because this is too small, basically. So what we are dealing with now in many processors it's 32 bits, and even some are 64-bit. But in this course, we are using 32 bits, and what we are using in MIPS is going to be 32 bits. So this is kind of like the pattern that we have for our addresses. It start from 0. The next one going to be 4. So we are jumping basically by 4. The next one going to be 8, and then C, which is 12. And then we add 4 to that. That's going to be 16. So in hex going to be 1, 0. So this is our pattern always. 0, 4, 8C. And then this is 1, and then again going to be 0, 4, 8C. It's always incrementing by 4. And if you look at the content here now, we have basically 8 digits in hex. So that's 8 digits. Each of them is 4-bit. So 8 times 4, that's 32 bits. So this is 32 bits then. And again, 32 bits. So basically, that's the layout of the memory that we are dealing with now.